Wine. I've been doing research on color behavior in red wines for some 20-odd years and still don't have the answer. But I have patience anyway. Well, there are a number of things that can affect the color stability in red wines. Of course, as you know, the primary reactants are pigments, polyphenols, that is non-pigment phenolics, and aldehydes. Those are the primary reactants that affect the color stability. And some of the things that are formed, of course, are oxidized pigments. Oxygen is one of the main enemies of color stability in red wines. You can form pigment polyphenolic fractions or complexes, polymers, whatever term you want to use. And you can also form polymers by the interaction of pigments and acetaldehyde. So the factors that affect color stability are the grape, the operations performed on the must, the fermentation, and of course the conditions and operations to which the wine may be subjected after it's made. I'm going to go over some of these things, give you illustrations by means of a couple of tables. The variety of grape is an important factor. If you refer to that table 1, you see that Alicante Boucher lost 69 4/10% of its color in 9 years. Charbonneau 47.3, Carignan 37.3, and Valdopino 17.7. And of course the Tintoures, of which Alicante Boucher is probably the best known of them all, those grapes having colored pulp, are notoriously unstable as far as the color is concerned. Very easy to extract the color because the color is in the pulp as well as in the skins. They're usually heavily colored, but the color is definitely unstable, as the data in this table indicates. In addition to the color loss in these various grape varieties over a period of years, varietal differences are also responsible for differences in the other phenolic materials that are present in the wines. That is the non-pigment phenolics. And in the amounts of the various acids, which also had an effect upon the color stability, and the pH, which is a decisive factor, and to some extent the pectic materials. So variety definitely plays a major role in color stability, everything else being equal. Now the effect of season on color loss during aging, given in table 2, that's the percent loss in 8 to 10 years. In 1936, 65% loss of the wines that were made in 1936. In 1937, wines made from the same grapes, 30.3% loss. In 1938, 23.8% loss. Well, you can see there's over double the loss in 36 as compared with 37. 1936 was a very warm year. So everything else being equal, the warmer the year in which the grapes are grown, and the wine is made, of course, the less stable the color will be. And that is attributable, among other things, to the fact that the warm years you'll have a higher pH, you'll have a lower tannin content, and of course the lower acid content, with pH and tannins playing rather major roles in the susceptibility of this color to dissipate. Now there are a number of operations that can be performed on the must. One of the fairly common ones, not as common now as it used to be, thank goodness, is heating prior to fermentation to extract color from the skins. This is done in one of several ways. One of the simplest ways is to crush into a tank, draw off the juice, put it through a heat exchanger, and pump the hot juice back over the cap until such time as the whole contents of the tank are brought up to 120 to as much as 140 degrees Fahrenheit. That probably does the most damage to color stability of any method of heating that we know of. Another method is to put the crushed grapes, pump the crushed grapes through heat exchangers, and bring the whole mass up to anywhere from 160 to 185 degrees, hold it for about 2 minutes, and then cool it down by countercurrent flow. And then separate the juice from the skins after a period of an hour or so, and then ferment out the juice and handle it like a white fermentation thereafter, except that the fermentation temperature would be in the usual red range of 70 to 82 degrees Fahrenheit. Because we found by experience where we have gotten color by heating the crushed grapes, separating the juice, if we ferment that juice at the white wine temperature range of say 50 to 55 or 60 degrees Fahrenheit, we get something that is quite different from the usual red wines. It tastes and smells more like a fortified grape juice than it does like a fermented red wine. But if we ferment this at 72 degrees, then we produce a conventional type of red wine. The French and the Italians particularly, also to some extent the Germans and the Swiss, have recently, as in the last few years, gone into various intricate systems of color extraction of reds, used in very elaborate systems in an endeavor to every year produce a well-colored wine. And of course they have a different problem we have here, because quite often, due to the climatic conditions prevailing during the ripening season, the grapes have become more or less infected with Botrytis cinerea, the noble rot, and as such become badly oxidized, and the color would be very, very low. So by using a heat treatment, they will kill the enzymes produced by the Botrytis cinerea and will largely prevent the oxidation that's promoted by the action of the Botrytis cinerea growing on the grapes. We've tried various methods of heating here, and to the best of my knowledge, and I've done an awful lot of work on this research over the years, a heat-treated must or grape invariably produces an inferior table wine and invariably produces a superior port. And that's understandable, because one of the chief problems in making port is the fact you only have a very limited contact time of juice with skins to extract color. Didn't intend to digress so far on this. Well, I think you gathered from what I said that I do not favor the use of heat for color extraction. Fermentation temperature, amount of SO2 added, yeast strain that's employed all affect the color stability. Naturally, a hot fermentation temperature, particularly if the fermentation sticks, is going to have a decided effect upon the color stability. And the amount of SO2 added, we've done quite a lot of work on that, and we found that adding up to 250 parts per million of SO2 increases the color stability. I will admit, adding 250 parts per million of SO2, you have to wait quite a long time for the fermentation to start. And unfortunately, it does produce quite a lot of acetaldehyde, so much so that it's detectable organoleptically. So I do not recommend 250 parts per million of SO2, but if you're interested only in color, go ahead and use 250 parts per million of SO2. But ordinarily, the 75 to 100 parts per million will do a good job of ensuring later color stability. Well, there's conditions and operation to which the wine may be subjected. Aeration, of course, that can lead to oxidation. Clarification can remove more or less color and can contribute to increase in color stability by removing unstable color. Refrigeration, the same thing. Refrigeration, you can coalesce the color particles to make them large enough to be removed either by precipitation or by filtration. That's the unstable color matter. Filtration, of course, to remove the particles large enough to be removed by filtration. And sunlight has a bad effect on reds as it does on whites. No. Pardon?
Any particular wavelengths?
Yeah, the ultraviolet is bad. The same as with whites. Any question what I've covered so far?
What kind of stability would you get by dipping whole grapes in the boiling water for a very short period of time? You're supposed to expect quite a bit of color.
You need to immerse them for about 2 minutes to get good color extraction. And the color stability is quite reasonable. We developed a method for heating whereby we put the grapes as they came from the field into a closed pressure chamber and introduced steam at 50 pounds pressure, which I think is around 277 degrees Fahrenheit, for 10 seconds, and then exhausted the box. And that does about the least damage to quality and to color of any method of heating that we know of. And still, we were not able to make consistently equal quality wines. In fact, consistently, we were less quality as far as dry reds were concerned. Well, the principal instability reactions are one, oxidation of pigments, which of course will destroy color. If the pigments oxidize, the color is destroyed. Reaction of aldehydes with pigments that I mentioned earlier. Polymerization, which can both stabilize color and it can also cause color loss depending upon how far it goes. If the polymer becomes too large, it will drop out. But up until the point that it ceases to be soluble in the wine, polymerization is usually a stabilizing influence on color rather than an unstabilizing influence. And hydrolysis of sugar. The pigment molecules in vinifera grapes all contain sugar at the 3 position. And as long as the 3 position occupied by a sugar molecule, the pigment is quite resistant to attack by any number of disturbing agents. Once the sugar is hydrolyzed off, then the molecule is subject to attack by practically anything that you want to mention, and becomes so unstable that we have never been able to demonstrate the presence of aglycones, that is the sugarless molecule, in red wines. So those are all the things that can contribute to a decrease in color, or you might say are called unstabilizing influences on color. Tannin and SO2, of course, are stabilizing influences. Now a few words on the reaction of aldehydes with pigments. Acetaldehyde, of course, is a usual constituent in wines. The amount there generally depending upon the amount of SO2 that's present during fermentation and also upon the temperature of the fermentation and so on. SO2, as you well know, complexes aldehydes. So the more SO2 that you have present during fermentation, the more aldehydes you're going to have at the end of the fermentation, everything else being equal. It inhibits aldehyde formation, but because of the fact that it favors accumulation by complexing of the aldehyde, on the whole, the addition of SO2 is going to result in the formation, or I should say the retention, of more acetaldehyde at the end of the fermentation if SO2 was not added. And of course, it'll slow the reaction right between aldehydes and pigments, but as was pointed out in the oxidation, all it does is slow it. It does not prevent it. Well, minimizing color instability, if you have a choice, select grapes with a low pH, have an adequate tannin content, and avoid those varieties of unstable color. That is if you have a choice. Don't heat much for color extraction, and ferment between 70 and 82 degrees Fahrenheit, or even 84 degrees Fahrenheit. Avoid aeration, store at moderate temperatures, and maintain low metal content. Clarify with bentonite, but only if necessary. Don't routinely clarify with bentonite in red wines, because a bentonite clarification will remove more or less coloring matter, and it will remove stable coloring matter because of its adsorption properties. So don't clarify with bentonite unless you find that you're going to greatly improve the later color stability. In other words, there's enough unstable color material present that it pays to add bentonite to remove a good part of this unstable coloring matter. And of course, as the cold causes coalescing of the unstable color particles, those particles later on are going to fall out. It's recommended that the wines be refrigerated to allow the particles to coalesce to the point where they are large enough to either fall out or to be removed by filtration. And keep SO2 at around 75 parts per million during storage, and add anywhere from 15 to, in the case of fairly unstable wines, that as far as color is concerned, up to as much as 35 parts per million of Bali. Any questions before I go on to the color chemistry?
Which red varieties do you consider to have the more stable colors?
Petit Syrah, Cabernet, Barbera, they're all very stable. Zinfandel is pretty stable. Well, let's, yes?
Why does heated must have a higher pH?
Pardon?
Why does a heated must have a higher pH?
A heated must?
Yeah,
I didn't say it did.
I've read it does before. I was just asking why that's.
I don't think the heating is going to have any effect upon the pH of the, oh yes, I'll take it back, it will too. You're right. Because you extract more potassium. You're absolutely right. You extract more potassium when you heat, which is going to lower the acidity and raise the pH. Any other questions?
Is it known the chemical difference between the color compounds that are extracted by the normal fermentation process and those that are extracted by heat? Or
The color compounds that are extracted are the same
why is one unstable and the other not?
because of the oxidation that the juice suffers during the heating.
If one could avoid oxidation during heating, it could get stable compounds.
We have pretty good indication that if one can avoid oxidation during heating, that the deleterious effects of heating are greatly minimized. In fact, it's such good indication that I've arranged for special equipment to try it out this fall. Yes?
Dr. Singleton was talking about a pressure tank that they use for heat their color extraction. They bring the pressure up to so much inside that the CO2 is actually dissolved in the juices within the cells. And when the pressure was taken off very fast, it ruptured the cells of the skin.
Right.
Extracted color.
Yeah, I saw that type of fermenter operating in South Africa in '67 when I was there. And I was quite impressed with the wines produced by it. We came back here and tried it, and it didn't work. Don't know why, it didn't work. Allow the pressure to build up to about 40, 45 pounds, then an automatic valve will crack open at that point. I say crack open, you use a 2 to 3 inch valve depending upon the size of the tank, and the gas just rushes out from the top of the tank, and the whole tank just boils. Everything that just boils like this. And of course, depending upon the rate of the fermentation, this will crack anywhere from 1 to every 4 hours. But we tried it, I think, 3 different years and had no success with it. Maybe we didn't have the green thumb, I don't know.
good color extraction, or just didn't work?
The color extraction was inferior and the quality of the wine was inferior to the control wines made by the punching down method.
How does the carbonic maceration technique affect post-filling?
We've tried that too for a number of years and never been able to duplicate the success that the French claim for it. However, we have never worked with commercial-sized lots either, and that may be the difference. We only worked, I think, 50-gallon lots is the largest we worked with, whereas they work with multiple 1,000-gallon lots. I think 1 or 2 wineries in the state are planning on trying that this year with 5 or 10,000-gallon tanks. Any other questions? Well, refer to this. I suppose you're all up on your pigment chemistry. But in case some of you need a refresher, I'll go into an explanation in some detail. The top left-hand figure there shows the basic structure of a grape pigment. You notice that you have 2 benzene rings that are connected by the C3 residue, the heterocyclic ring containing the heterocyclic oxygen. In other words, the oxygen is in the ring itself. It's not attached to the ring. That is the basic structure of a wine or grape pigment molecule. And you'll notice that the numbering starts with the heterocyclic ring and proceeds clockwise. 2, 3, 4, and then into the benzene A ring, 5, 6, 7, 8. And the same thing on the B ring. It starts with 1, but we use prime numbers so we can distinguish between the A and the B ring. And 1, 2, 3, 4, 5, 6 are the prime numbers on the B ring. The figure just opposite that is for malvodin, which is the pigment usually found in the greatest quantity in vinifera grapes. As an average, about 45 to 50% of the pigment that's present in vinifera grapes is malvodin. And this is called a favilium chloride. It's also called an A-glycone, or another term that's used to describe this is anthocyanidin. And that is a pigment without any sugar attached to it. If the sugar is attached, then the corresponding terms, instead of aglycone, glycoside. Instead of anthocyanidin, it's anthocyanin. No sugar. And sugar attached. And in vinifera, the sugar is always attached at the 3 position. And if you have the 3 position filled with sugar, then you have a monoglucoside. And if it happens to be malvodin, then the full name for the molecule with the sugar attached would be malvodin 3-monoglucoside. Malvodin to denote the type of pigment, 3 to denote the attachment of the sugar, and the glucoside to tell you that the 3 position is occupied by a sugar molecule. Now, in non-vinifera grapes and in hybrids that are produced by crossing vinifera and non-vinifera grapes, they have diglucosides. And diglucosides have sugar molecules attached at the 3 position and also at the 5 position. So diglucosides, sugars attached at the 3 and the 5. Monoglucosides, sugars attached only at the 3 position. Now, vinifera grapes contain only monoglucosides. Non-vinifera grapes like rupestris and our well-known Concords and so on of the East Coast contain mainly diglucosides. And that's one of the easy ways of telling in grape juice and in new wines what the grape was that was used for producing the wine, whether it was a straight vinifera or whether it was a non-vinifera or a hybrid, which is a cross between a vinifera and a non-vinifera grape. And some countries bar the importation of wines containing diglucoside, Germany for one. So there's been developed a very simple chromatographic procedure for showing the presence or absence of the diglucoside pigments. Now, in addition to sugar molecules being attached to the sugar molecule is usually an acyl group, in other words, an acid group. Not always, but quite often, in fact, it's very common for an acid group to be attached to the sugar molecule. And if there's an acid group attached to the sugar molecule, then they are called acylated pigments. And the 3 common acids found are cinnamic, caffeic, and acetic. And they're hooked to the sugar molecule. And these acids are quite unstable. They're easily hydrolyzed off of the sugar molecule, so it's quite common to find after the wine ages a bit that most of the acylating acids have disappeared. And it's also common to find after a period of time that you've had a decrease in the amount of pigment due to the hydrolysis of the sugar molecule. And of course that happens and the pigment molecule disappears very quickly. In fact, rate determinations have shown that ordinarily if the pigment is hydrolyzed, the sugar removed, that it disappears usually within an hour or 2 after the hydrolysis action is completed. So that's why we've never been able to demonstrate the presence of the non-sugar bearing pigment molecule in wines. Now, in addition to the pigments, I want to talk a bit about some of the non-pigment phenolics. Catechin. You'll find that immediately below the basic structure for the pigment molecule. That's a monohydroxyflavan. And it's one of the most common, one of the most abundant of the phenolics, non-pigment phenolics that are found in grapes. Leucocyanidin, just opposite the catechin. That's a dihydroxyflavan. It has the 2 hydroxyls at the 3 and the 4, whereas the catechin only has a hydroxyl at the 3 position. That's also very common, very abundant, usually in grapes and juice and wine. The leucocyanidin has this feature that if it is heated in the presence of a strong acid, the hydroxyl group is removed from the 4 position and the hydrogen from the 3 position, and it's therefore transformed into the corresponding pigment. And this can be demonstrated very easily. Take grape juice or a new wine, heat it with some hydrochloric acid, and you'll get anywhere from a measurable to a great increase in red color, because you've transformed the leucocyanidins that are present into the corresponding pigments. The reason I'm bringing up the catechin and the leucocyanidins is because they're intimately involved in the pigment behavior. The catechins, remember in the oxidation lecture, I said were the principal substrate for browning. It's because they're so reactive. In the case of pigments, they are the principal non-pigment phenolic reacting with pigments and other materials, as is leucocyanidin to almost an equal extent. Now the effective pH, and pH is very, very important as far as the color of a wine is concerned. As you can see from looking at the figures below the catechin leucocyanidin, that an equilibrium is established in a wine, an equilibrium between the two pigment forms. You have the colored pigment form, which is noxonium salt. You have the non-colored pigment form, which is called a pseudo-base. And pH determines the percentage of the total pigment material that's in the colored or colorless form. As the pH is decreased, more and more of your pigment is transformed into the colored form. As the pH is raised, more and more of your pigment is transformed into the colorless form. So the lower the pH of the wine, with an equal amount of pigment present, the more visual color you will observe in the wine. And you can prove that for yourself by just taking any red wine, dropping in a little hydrochloric acid, and noticing the big increase in the red color. Or if you want to go the other way, drop in some hydroxide and notice the decrease in color. So pH is one of the determining factors as to the amount of color. It's going to be visual color that one is going to see in a wine. If you do drop hydroxide or any other alkali into a wine or into a juice and raise the pH up to around 5.4, you will pass through a region where you will have no color. And I think you probably all noticed that when you've been titrating for total acidity in red wines, that you will pass through a region where you have just a gray color. And then if you observe closely, you will pass through another region where you have a violet color. You'll go from a gray to a violet color. And around pH 5.4 is where this violet color occurs. And that's due to the fact that at that pH, you form what is called an anhydrous base form of the pigment molecule, which is violet colored. But with the pigments containing the sugar molecule, this is only a very fleeting or transient phase, and the violet color fades very quickly, even if you maintain it at pH 5.4. With the aglycones, those molecules from which the sugar has been hydrolyzed will maintain the color for a period of 2 to 3 or 4 hours. Any question on this pH? Okay. Now the effect of sulfur dioxide. Look at the set of figures below the effective pH. Like the effective pH, sulfur dioxide can cause a pigment to exist in two forms, a colored and a colorless. As the sulfur dioxide content is increased, more and more of the pigment is changed in the colorless form. And this is due to the bisulfite adding on at the 2 position of the pigment molecule and destroying the resins and therefore rendering the pigment colorless. And I think most of you have had the experience of adding sulfur dioxide to wines or juices and noticing a decrease in color. And that's due to the fact that the sulfide will add on to 2 position and cause the pigment molecule to become colorless. Now, the lower the pH, the more pigment is in the form that reacts with the sulfide, as you can see from looking at the reaction there. But there's another factor working also. This is the part of the molecule that must react with the pigment. Even though when you lower the pH you have more in the pigment form that reacts with the sulfide, as you lower the pH you're shifting more of the sulfide over to the sulfuric acid form and making less and less of the SO2 that's present available for reaction because it's in the wrong form. So much so that at very low pHs, say around 1 pH, the sulfur dioxide has very little effect upon decolorizing because practically none of the sulfur dioxide at that low pH is in the bisulfide form. So again, pH has an effect in modifying the action or decolorizing action of sulfur dioxide. This all clear?
It's drawn like it's not reversible.
Pardon?
Is it reversible?
Yes. Unless you use too much sulfur dioxide. I've played around with that for quite some time, and I find if you go into extremely heavy dosages of sulfur dioxide, up to say 1,000 parts per million, very little of the color can be regenerated when the sulfur dioxide is oxidized. And if you go to 2,000 parts per million, you will regenerate none of the color. But up to 500 parts per million, you will regenerate most of the color that is lost by the action of the sulfur dioxide. Any other questions on this? Okay, effective acetaldehyde does have a definite effect upon the color behavior in the wines. And that's because the acetaldehyde can add on at the preferred 6th position or the 8th position. Look at your basic structure molecule there. The 6th position is the reactive position, 8th position, reactive position. The acetaldehyde can add on. Now look at the bottom formula there on that page. Acetaldehyde plus pigment molecule. You notice the acetaldehyde in this case is added on at the 6th position. That in turn reacts with another molecule of pigment or non-pigment phenolic, and you'll get an addition product with the acetaldehyde bridging to the 8th position of the 2nd molecule. And we have definite proof that this occurs in wine, and it's one of the big factors in the color behavior in wine. Because the acetaldehyde, and even more so formaldehyde, which of course is not a natural constituent, does have a decided effect upon this bridging or polymerization. And this reaction can continue indefinitely. You can form a dimer, trimer, tetramer, and so on, up until the point where the molecule becomes so large that it can no longer remain in solution and will fall out. There are other places where the addition can take place, the 4 position and the 2' and 6'. Though the 4 position is not a favored position because with the sugar molecule on the 3 position, you have steric hindrance, and it's very difficult for the molecules to approach close enough together to react. And other favorite combinations are between the 6', 8, four, 8, 6', 2', and 6 and 8. And these are acid catalyzed oxidations, where there's a direct coupling between the 2 molecules, either pigments or non-pigment phenolics or mixture of pigments and non-pigment phenolics. And a very interesting effect of this polymerization is that we get a change in the response of the pigment to pH. Now, with a pure pigment solution, the pH response is well known over the usual pH range. In fact, there are tables published as to the amount of color increase as the pH is dropped for a number of the individual pigments. Now in wine, which is a complex mixture and where you have more or less polymerization, and the older the wine, the greater the polymerization, as these molecules become involved in polymers, either polymers formed entirely of pigments, but more usually formed of pigments plus non-pigment phenolics, these polymers, the pigment in them is non-pH responsive. And that is one of the major factors that is responsible for color behavior. Because if you look at the pH response curve for most of these pigments that are commonly found in vinifera grapes, you'll find that at the higher pH ranges, say around 3.8, 3.9 up to 4.2 or 4.3, and we do have wines run up as high as 4.4, they should be practically colorless because very little of the pigment is in the colored form at that pH. I think at 4.2, if I remember rightly, on about 5 or 8% of the pigment that's present is in the colored form. So at these high pH levels, wines, red wines, at the most should be a very, very light rosé in color. Instead of that, quite often they're very, very heavy colored. And that's due to the fact that so much of the pigment is in the polymeric form and as such is not responsive to pH. In other words, it remains colored regardless of what the pH of the wine is. Any questions? Okay, that's it.